This video is going to go along with the homework 2 from chapter 7, and it's on page 2. So it says an opinion poll asks, are you afraid to go out at night because of crime? And it says the people who said yes, the proportion was 40% or 0.4. So I'm going to circle that here, and I'm going to write that as a percent. 40% said yes. And it sounds like that is the proportion of all adults. So that number is actually called a parameter, because it sounds like they're using the word all, which means that it comes from the population. So the proportion of all adults in the entire population who say that they're afraid to go out at night is 40%, which is kind of scary actually. So now we're going to do a sample. So the sample is n equals 20. So write that down. And we are going to do a simple random sample, SRS, and we're going to do it using a table of random digits. So this is actually review from when we did SRS with a table of random digits. So it says, be sure to explain clearly which digits you use to represent yes and no. So if you remember when we did simulation, we would create a key, and we would let certain digits represent one phenomenon and certain digits represent the other phenomenon. So we have 40%, and that's going to be yes, and the complement of 40% is going to be no, which is going to be 60%. So what you have to do is you have to let 4 digits out of 10 represent the 40%, which is yes, and the 6 out of 10 represent no. So if you guys remember, we're going to let 0, 1, 2, and 3 represent yes, because that actually is 4 numbers. And then the rest, 4 through 9, is going to represent no. Okay, so if you count the digits, remember from 0 through 9, you would have to include the 0. That's actually 10 numbers. So 0 through 3 is 4 numbers, and 4 through 9 is 6 numbers. So that's why I did the 40% and then the 60% breakdown, okay? So now what I'm going to do is I'm going to use the table below, and I'm going to write directly on the table below to carry out a result of a simulation. So I'm just going to use row 1, and I'm going to categorize each digit as either yes or no. Either they are afraid or they're not afraid, okay? So the yeses are 0 through 3, so I will circle those. So there's 5, 10, 15, 20. I'm actually going to stop here for trial number 1. Okay, so I'm going to circle all of the yeses. 2, 3, 4, 5, 6, 7, 8. Let me double check. Okay, it looks like for trial number 1, I had 8 out of 20 digits, because I did 20 digits because n was 20. That's the sample size. And that is going to be my first p hat. So p hat is a sample proportion. And a sample proportion comes from a sample, so it's called a statistic. Okay, so the first p hat I got was 8 out of 20. And if I wanted to divide that, that is going to be as a decimal 0.4. So my first sample actually was exactly equal to the true population proportion of 0.4. Now I'm going to do it again for row 2. I'm going to do 20 new digits. So I'm going to do 5, 10, 15, 20, and I'm going to circle the ones that are yeses, for the 0 through 3s. Okay, so let's do it. Okay, so it looks like I got 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 out of 20 again. That's going to be called p hat 2. So that is a separate simple random sample of 20 digits that were random. So simple random sample. And I found the separate sample proportion. So now I want you guys to stop the video and do line 3, line 4, line 5 right now on your own. Okay, so for line 3, I got 8 out of 20 again, which is 0.4 for p hat 3. For line 4, for the sample proportion, I got 10 out of 20, which is p hat 4, which is 0.5. And for the last line, I got 5 out of 20, which is p hat 5, which is 0.25. So I got all the p hats. I got every line, the sample proportion of yeses. So now what I'm going to do is I am going to find the mean of all 5 of my sample p hats, okay? So the mean of all the sample p hats means I'm going to just add them up and divide by 5. Now, I really shouldn't use the symbol mu here because I only did this 5 times. I would only use a mu if I did this infinite times, but it's okay. So basically what I'm going to do is I'm going to do 0.4 plus 0.4 plus 0.4 plus 0.4 plus 0.5 plus 0.25, and whatever I get, I'm going to divide by 5. So we're going to do this now. So I added them all up and I got 1.95, and when I divided by 5, I got 0.39. So the mean of all the p hats I got was 0.39. Now notice that the true proportion that they claimed to be scared of going outside, the true proportion, p, which is called the parameter, is 0.40. So do you guys see how close 0.39 is to 0.40? And I actually only did this 5 times, and I got a mean of all the p hats very, very close to the true proportion. So this is showing you that the sampling distribution of p hat is centered around the true proportion. So remember, a sampling distribution is all the values of the sample statistic. So basically we would just plot all of them, which I'm not going to do for the sake of time, and this is called the sampling distribution. The sampling distribution, in this case, of the sample proportion, which is called p hat. So if this sampling distribution is centered very close to the true parameter, which is p, then this is called an unbiased statistic. The p hat is called an unbiased statistic, okay? So down below it says for number 3, the sample distribution of p hat is the distribution of all possible samples of the same size. What should be the mean of this? The mean mu of all the p hats should equal the true p, which is 0.40. And then I use a mu instead of a p. Okay, so you could skip this part down below, but here is the main concept of this video. It's that if the mean of all the sample statistics is centered at the true value, this is called an unbiased statistic. So on the next page, it says unbiased estimator. Another name for an estimator is a statistic. Basically what it means is the statistic is centered at the true parameter value. Okay, so in the case of our example, the mean of all the p hats should equal the true parameter p. And our example from yesterday, the mean of all the x bars should equal the true mean mu. So basically I want you to think about unbiased, think about it as like a bullseye. If you are centered at the bullseye, you're centered at the true parameter. So picture these bullseyes, the center is the true parameter. And if it's in the center, it's centered at the true parameter. And if it's off to the side, it means that the statistic is biased, okay? So letter A, you see it's not centered at the center, so it is biased. It is highly biased because it's not centered in the true parameter, it's off to the side. But you see B, it's centered around the true center, it's just spread out, so that's actually called low bias because it's centered in the center. C, they're all off to the side, so this is high bias because it's not centered in the center. And then D, they're centered in the true center, so this is low bias. Now ideally for a statistic, we want low bias, meaning it's centered at the true center, so centered at that bullseye. And the other thing that we want is we want low variability. We want low spread. So we don't want our values to be all over the place. We want them all to be clustered together. So A actually, even though it's biased, it has low variability because they're all close together, meaning they're all tightly spaced. B, even though it's low bias because it's centered around the true center, it's got high variability because it's all spread out. C is the worst one because this one is biased because it's off to the side, and it's also got high variability because it's over this, it's all spread out. Sorry, it's all spread out. And the best one that we want is D. This one is the best case. It is centered at the true center, so it's low bias, and it's all clustered together, so that's low variability. This is our ideal scenario. Low bias, low variability. So picture that bullseye centered at the true center and not really spaced out. So here's the AP example. It says 5 estimators for the parameter being evaluated. The value of the true parameter is 0. So write that down. True value of the population value is 0. We take simulations of 100 random samples, so we do it 100 times, each of the same size n drawn from this population. For each simulated sample, the 5 estimates, that's called n equals 5, are computed. The distribution, the histograms show them below, which simulated is the best estimator for this parameter. So they're telling you that the true value of the parameter, which is the population number, is 0. So ideally, we want it to be centered at 0. So if you take a look at these choices, A is centered at 0, B is centered at 0, C is not really centered at 0. It's centered at like maybe 2-ish, so I'm going to cross that one out. D is not centered at 0. It's centered at 2, so I'm going to cross that out. And E is not centered at 0. It's centered at like -2, so I'm going to cross that out. I want something that is centered at the true parameter value, which is 0. So which one is centered at 0? Both A and B. But the other thing that I want is I want low variability. So I want it to be the least spread out. So which one is less spread out, A or B? I'm hoping that you said B, and you're right. This one is the least spread out, which means the lowest standard deviation, and it is centered at the true parameter value, which is 0. And that is it. Thank you for listening.